Talk about provisioning the HashiCorp stack on cloud infrastructure. Thanks, James.
Okay, okay, cool. I can be heard. So the original title of this talk, so there's a good question that comes out of this slide, which is why is someone from Joyent talking about running HashiCorp infrastructure in AWS? The answer is that until when the title was written, I actually worked at HashiCorp. So that's why. And I just changed like the 3 slides or whatever it was. So the genesis of this talk is effectively the work that I did at HashiCorp with a lot of other people to retrofit the best practices that emerged from people running console at scale and in production back into our own stack. Because of course we were running like pre-release versions before anything was stable, that kind of thing. And we kind of like never got around to fixing it until we made some time to do it, right? Because that's just the way things go. So once you've got the HashiCorp stack running, then applications are really easy to run, right? You can secure them pretty easily, you can submit new versions of them, that kind of thing. But the less explored side of this is how you actually get the stack running in the first place. And it's especially not well explored from an automation perspective, because what people are most interested in when they're first looking at it is how do I get this thing running quickly so that I can start looking at the APIs and see whether it can deliver value sort of to your actual business problem. And second, like installation environments are really different. So what worked for us in AWS probably doesn't work for someone in, say, Google Cloud or in Azure or on bare metal, which is an increasing segment of the market. So we're going to mostly talk about AWS today, and I'm going to present specifics of the automation that we were using to run Consul, Nomad, Vault in AWS, specifically for Terraform Enterprise. Despite having changed company, I guess I should probably do the quick plug. So HashiCorp and Joyent have a pretty good relationship. So we operate a public cloud and lots of private clouds. We got acquired by Samsung to run the clouds for Android systems for Samsung. And we've been using HashiCorp stuff there for a long time. And our autopilot pattern in particular leverages Consul and Vault particularly. If you look at autopattern.io, then you'll find a whole bunch of different self-assembly things for legacy applications primarily, things that everybody has to run but no one really wants to run. And the reason for that, there's lots of choices of tools, but the reason we really like the HashiCorp stuff is the library approach. So you can broadly divide infrastructure into 2 categories, right? You either have frameworks or libraries. And in frameworks, you put your code inside this thing and it calls you when it wants. And for libraries, you can sort of compose what you need and you're in control. And the HashiCorp stack is a particularly great example of library thinking versus framework thinking. So if you want to take, say, Vault and just Vault, then you can do that. If you want to use Consul, but you want to run like a different secrets management system on top of it or a different scheduler, you can do that. And we really value that approach because trying to move everything at one time is hard work. Finally, the final sort of plug, I guess, is so Nomad in particular is deserving of some attention. There was some great new features in it. And we've been extending Nomad at Joyent. We have our own operating system called SmartOS, which is ultimately a derivative of OpenSolaris. One of the things that we found is people really want to run scheduled containerized stuff on bare metal. And Nomad and SmartOS very, very well suited to each other. Not being limited to Docker is a huge deal for us. So we can implement zones, which are the original container, if you like. And excellent, someone's heard of it. And various CFS features to great effect. Those bits will probably get upstreamed at some point. We're currently working in a downstream fork. But I see Alex nodding, so that's a good sign that at some point it will be available more generally. So enough with slides. I'm just going to show code, mostly because I didn't have time to write many slides. This repository, for anybody that wants to look at it, has all of the code that I'm going to talk about. I have the infrastructure running right now. I'm going to extend it a bit more over time as various things come out. Okay, actually there were 2 more slides. So what are we trying to do? So the HashiCorp stack's cloud agnostic. But bootstrapping is a really environment-specific problem. We want to use the features that the platform makes available to us to get it bootstrapped in a secure manner. So in AWS, we make heavy use of KMS, and even though we're using Vault ultimately for secret management, there's some initial secret zero problems where we can take advantage of the platform to deliver that. AutoScaling groups, we can use in AWS. They vary in their implementation across every platform. But by specializing this stuff, we can do a really good job of automating everything. We're aiming for self-assembly and self-healing. So as an operator, I don't want to get paged because an expected event, which is a server went down, happened. Right? If it happens at 3 a.m., I don't care. A new one should come up. It should join a cluster. I shouldn't have to. I might get a Slack notification about it that you can look at in the morning. But that shouldn't be, unless something goes horribly wrong, then that shouldn't be a pageable event. It's expected. So we're going to look at using Packer to bootstrap Linux from scratch. We're heavy believers, or everywhere really, in the ZFS file system. Ubuntu recently shipped with ZFS and systemd, and I know it's a controversial opinion, not least among Joyent employees, but systemd is the best thing that's ever happened to Linux, in my opinion. It's the first time anyone's ever gone through and applied some actual systems thinking and made something that works consistently and in a manner which is you can reason about. And it's finally cross-distro as well. So we're going to look at Ubuntu built from scratch with ZFS and systemd. In particular, if you're running in the cloud, then the images are kind of you have no idea what's in them. Being able to bootstrap them from scratch is a really important step to being able to secure what you have because you at least know what's there and you can start properly. My final point, use ZFS everywhere. Why? So this down here is the output of the zpool status. So zpool is the ZFS storage abstraction. This is running on EBS. It was actually while I was putting this talk together. I'd never seen it happen before. But it turns out that once you've seen it once, it happens quite often. This is EBS corrupting data. So I give it some bits. It gives me different bits back, quite happily. Now, it turns out all storage does this, and there seems to be some rule that the more expensive the storage, the worse it is at actually corrupting all your data. But EBS, despite Amazon's claims, it does corrupt data. And ZFS has this system for checksumming built in. So every block gets checksummed, and the entire file system forms a Merkle tree. So you can detect exactly if something that was read back is not what was written. And it will report it back, and if you have an appropriately configured disk array, then it will just heal everything for you, and you never have to care about it. There are some operability benefits as well. So, okay, let's get to code. That's more interesting. So what we're going for, I'm not going to talk about the entire stack at this point because it's kind of a lot of work. The code is all there and will continue to be there. But so right now what we're going to look at is Bootstrapping Console from scratch. So we can start from an empty AWS account and look at all of the steps needed to bootstrap the account with appropriate permissions, where you look at the AMIs that we need to build, you look at the infrastructure we need to build, the certificate management we need to build. What we're not going to do is aim for a single Terraform apply to create everything, because it's great for demos. It's actually not that realistic in the real world. Applications tend to be made up of layers of infrastructure, which are each independent states. Okay, so this is just the repository. I put the URI on board a minute ago. It's under my GitHub. And everything is contained in here. Whether or not you'd actually organize it like this in production versus separate repositories, kind of whichever you like. To make this approachable and easy to use from just a single checkout, it has code in there for creating buckets to manage Terraform Remote State. So Terraform Remote State is one of the features which has improved a lot over the last couple of releases of Terraform, and it's now a really useful way for collaborating. So it's a particularly common architecture to have, or team architecture, to have a central operations team responsible for things like networking and shared infrastructure, and then to delegate operation of particular applications to individual teams, teams who build them. And one of the things that you have to do there is share important state, right? So for example, what's the ID of the VPC that you're deploying into? What's the, which subnets can you use? What load balancer or what DNS record, DNS zones can you use? That kind of thing. And the shared state system, or the remote state system, provides a nice shared way of doing that. So if I give read-only access to the central state to an application team, they can make use of the values, and they'll get notified when they change. They don't have to keep copying and pasting values around. It's a really nice way of doing that. So what I'm not going to do is just like go through the steps one by one. There's a README file in the repository here, which literally lists every step of the process here. So anybody that's interested in the precise process can just can go read that. What I'm going to do is call out some of the patterns that are used instead. So the first thing we talked about was building AMIs from scratch. So there's a builder in Packer, fairly new one called the EBS Surrogate Builder. And what that does is launches a source instance with from an Amazon supplied image, attaches an EBS volume to it, does some bootstrapping, and then deletes the instance and creates an image out of the attached EBS volume. So what you can do is bring it up, bring up the source instance, chroot into, create a file system on the separate EBS volume, change the root into that, and then deb bootstrap effectively if you're on Ubuntu. So you can install Linux from scratch effectively onto that EBS volume, and then create an image from that EBS volume. And that's what that builder does. Useful Packer tip for people. Apparently not a lot of people have seen this. I don't know. I think it's relatively new. If you don't want to hard code AMIs everywhere, you can filter based on all kinds of different things here. Particularly useful is the name tag and then the most recent true. So most recent true will effectively, that will get you the latest Ubuntu 16.04 image for Amazon, and we'll keep updating that. Now, generally you don't want things to automatically update themselves in the background, but since we're only using this as a temporary measure, that's kind of fine. The other thing that's really useful is being able to, so Packer takes JSON, you can pre-process these things so that if you don't want to write JSON, you want to write something a bit more flexible, then you can just compile them in and Packer will read them properly. The actual mechanics of doing this, they're all there if you want to go read them, but it's not that interesting. The result of it is you end up with, if I go into one of these boxes, this one's running the AMI, for example. If I sudo z pool status, then we can see we have a root pool. If I sudo ZFS list, the entire file system is effectively in ZFS, which is nice for some things. So that's kind of our base image. And from there, like most people don't do that, right? People generally just use the AWS supplied Ubuntu images. There are some advantages to building your own. The next step in this thing is layering on top of that. So taking the Scratch image we built and applying some customizations to it. In this particular case, one of the things we want to do is tame CloudInit. CloudInit has like some nasty habits, and if you ever wonder why your instances take so long to start, the answer is almost always CloudInit. If you just, there's some YAML scripts that you can put in the user data that will just disable all the nasty parts of it. And most of them are doing things that you don't even need, like OpenStack provisioning. It's like, okay, fine, whatever. So the final principle for this part is we're going to deliver all of the software to our instances in operating system packages. So in this case, we're going to package console. We're going to package all the configuration that goes with it. And we're going to install them via apt-get. There are a few reasons for that, but one of them, in particular in security-sensitive environments, is you can audit the entire contents of a running machine to verify that the packages haven't changed underneath you if you do it via this means. There's apt-get verify. I think that's the command. And that will verify the entire file system. So the downside of that is it means we need to build some packages, and package building is one of these things. The reason no one does it is because it's terrible. And the tools are designed for people building operating systems, not for people packaging their own software. Fortunately, when it comes down to it, a package is pretty straightforward. It's an image of what you want your file system to look like and some metadata. So there's a tool called FPM. The PM stands for package management, and I will leave the F to the imagination. And you'll probably be correct. What I'm not interested in doing is building everything from source, because it's kind of a pain. So we're going to use the HashiCorp supplied binaries, verify the checksums, and we can be reasonably confident that these are the correct thing at that point. So the there's a whole system for packaging these things in the repository. It's not great, but it's not terrible. It's like the least worst option for delivering software onto a machine in a world of terrible options. So some of the other interesting things. Quite often, in particular for console clients, it's really common to want to wait for console to be available before you start other things. So particularly, like say Vault, you're going to point at console, and now Vault's written properly, so it will wait for console. Right? It won't just like crash out an error, but that's not the case with everything. So it's kind of useful to be able to orchestrate the boot state, the boot phase of the machine, so that if you have something that's foundational like console on the machine, you want that to be up before you even bother starting the next service. It's also useful because it means you don't get like a stream of errors at the start of every log for every service. So you can use systemd for this. There's a script that just sits there waiting for console to get a leader. If it's a server, that means it's part of a cluster. If it's a client, that means it's connected to a cluster so you can get the information about the servers. So systemd allows you to define targets, which are made up of services. So the services are, we're going to wait for this thing and then exit. The target console_online.target will be reached when the local console node is a member of a cluster. So in other words, when it's usable. So you can then tie other services start points, say Nomad, for example. If I were to look at the Nomad start here, where is that? Lib systemd system, nomad.service, we can say it requires console to be online before we even start it. This is the kind of stuff that's really hard to do without a target-driven initialization system, which is why systemd is kind of useful for this kind of thing. This is a similar one for Nomad as well. Authentication. So AWS has like a particularly limited system for SSH management. So you specify one key at instance creation time, Cloud Init pulls it down, sticks it in a directory, and then if you want to change it, then bad luck. And of course, you always want to change it because someone leaves or it rotates, or you have like this shared key that every employee has access to. Generally bad ideas. There was a post from Facebook about a year ago which detailed their mechanism for running an SSH certificate authority. So OpenSSH, a few years ago, grew this ability. So you give it, rather than the public key of a particular private key, you give it a public key with which, and you use the private key to sign other people's certificates. So you can present this certificate, and it will ensure that you're valid, that you can sign in with a particular username, a particular principal. And you can make these things, you can give them an expiry date. So you can issue really short-lived SSH certificates to people. You can tie them to their identity, but you don't have to manage lots of keys on every instance. So we can deliver the configuration, of course, in a package. Effectively, all you do is give, where are we? You give a trusted user CA keys thing, and then you give it the public key of this CA. Vault has recently grown the ability to issue these things. So if you're authenticated to Vault, you can issue, say, a 5-second valid certificate, which will log you into whichever instances you need. So you can't do it by hostname, sadly. That's a limitation of OpenSSH. But if you need to, you can deploy like different different certificate authorities to different zones of your infrastructure. There are ways around it. If you're interested in that kind of model, I'd strongly recommend reading the Facebook post about how they're dealing with their own infrastructure. One of the nice things about this approach versus individual keys or shared keys, and particularly shared keys, is it gives you a degree of non-repudiation. So the identity is tied to the certificate. The authentication log of the instance will show you exactly who presented the certificate, whether or not it was accepted, whether it was rejected, or whatever. And you can ship the authentication log off the box to, say, CloudWatch, and you can do auditing for unauthorized access of machines. So this would have been the approach I recommended up until last week. And last week I saw this actually really cool thing called Teleport. Oh, can't type. So Teleport is like this OpenSSH management system, and it will log every session. So the entire contents of every session will get logged and stored securely, so that you can go back and replay sessions and see exactly what someone did versus taking them on their word for it. That's worth an extra look. It uses the same stuff under the hood. So that's kind of all the base infrastructure. After that, we can start talking about individual applications. And so we've got an OS with our customizations applied. We've got a console package. And this is the part where you start specializing to the environment. So we want servers to self-heal, and the best way of doing that in AWS is to run them in an AutoScaling group. So if an AutoScaling instance disappears, then if you set the min, max, and desired all to the same number, then it will maintain a set number of instances for you. So this used to be hard to do with console because console would grow quorum indefinitely. And unless you managed which servers were there and which were not, you could lose quorum very quickly by having AutoScaling bring up new servers, take down old ones. You'd be left with, say, 6 servers listed in your peers file and only 3 available, less than n over 2, n plus 1 over 2, so you'd lose quorum. So console recently added some features which make this really nice. So where am I? In user share, 20 console. So what you can now do is this autopilot block. So clean up dead servers you want to be true, and then retry join EC2. You set it to the autoscaling group name, and then everything just works. The thing that I'm using to render this template has like built-in EC2 metadata support. It's got some terrible name that's hard to pronounce. This replaced, this file and that utility replaced 550 lines of bash, which was previously used to do this. Well worthwhile. The autopilot stuff so far appears to work great. In fact, we could probably look at it. So which box am I on? Console members. OK, not that one. So if I sign in quickly to a console server, SSH ops at whatever, sure. The ASCII art always takes longer than everything else. So if I console members here, then we can see this was assembled. It came up a little bit before this talk. And so we've got these servers forming a cluster. We currently don't have any clients in it. But if we go and terminate one, then we can see what happens when. Let's not terminate the one I'm connected to. Let's terminate this one. So what we should see, over the course of time, is that the autoscaling group will realize the instance is gone. We'll create a new one. The new one will join based on the autoscaling group name tag, and then it will force the old one to leave once some period of time is up. So what we should end up with is a stable console cluster that's not growing its quorum, has required no operator intervention to recover from. So this is the kind of outage which happens all the time in AWS. They move your instances around. They give you basically no SLA on them. It might be an interesting experiment, in particular with the new console enterprise features of non-voting members. It might be really interesting to try running lots of console servers on spot instances. It depends on quite what your appetite for risk is. I'm not sure I'd want to recover that after it went out, but sure, whatever. Interesting thought experiment. So let's go back to some of this. So the Terraform for doing this is fairly straightforward. There's a Terraform pattern which is not that widely known yet. So around Terraform 07 introduced this notion of data sources. So previously, resources existed. Resources had a full life cycle. Data sources only have the read component of the life cycle. So they're read-only sources which expose some information. So that's how remote state works. For example, you can pull in read-only information from other people's state files. You can also query AWS APIs and lots of other APIs as well. So prior to Terraform 07, the common pattern for using Terraform was that you'd have a module, and then you'd have a TF vars file. And the variables file would list, you'd have generally one per environment, so production, staging, US East 1, US West 2, that kind of thing. And that would list all of the values for the variables. So it turns out that Terraform 07 changed that model quite a bit. So TF vars file still works, but it's no longer optimal because you can't put data sources into a TF vars file. And quite often, all of the information is available to you to introspect given a single thing. So if you know, for example, that you're going to be in US West 2 and you're going to be in VPC X, then you can basically enumerate all of the other information. So subnets, routing, all that kind of stuff. You can discover yourself. You don't need to go and hard code all of that stuff. So the pattern that that we sort of developed for this, and certainly I've been recommending, I don't know whether it's a universal recommendation, is this idea of a composition root. So you have modules which, in effect, are very dumb. They literally take variables, have no data sources in them. They don't try to do anything smart. They just create resources. And then you have a composition root for each environment. So in this case, we'll have, I only have one because I did this demo quickly. You have one thing which then pulls in all of the information either from remote state, from hard-coded variables, or from other data sources, and does all of the work to figure out what needs to be delegated down into the modules from there. And the reason I call it a composition root is because you can compose multiple modules in this way. So in this particular case, for console, I have a module which is console itself, which will create all the auto-scaling groups, all the policies, that kind of thing. And I have another one, which is a system using Lambda to manage Route 53 registrations for auto-scaling instances. I'll talk more about that in a second. But there's a lot of information we need for this that would generally have been hard-coded before, either through variables with no explicit values, or in a TF-vars file, or via environment variables or whatever. And it was kind of a big job to manage all of that stuff, in particular between different environments. But now we can pull in remote state easily. We can pull in, you could do that before with a resource, but it was a lot less deterministic because you couldn't tell what those values were going to be. You can query AMIs using basically the same syntax as we were using in Packer with a slightly different encoding around it. We can generate things like the surf key we're going to use in console. So technically, you generally wouldn't want secrets in your state file. The reason we don't do that with TLS certificates, I'll explain more about them in a second. But the console surf encryption key is like the worst kept secret ever because it's on every node. So practically, it's there to prevent you, or my opinion is it's there to stop you accidentally joining two clusters together or joining a developer workstation into a production cluster versus for actual security. It's kind of like a checkmark feature. So we can just generate that randomly, and we can distribute it to DNS clients. So this kind of composition root pattern has become really useful. The layout of production repositories tends to be, you have modules specific, which are generic and reusable, and then you have a composition root per environment or a composition root per region with specific values or specific sources of values coded into there. It tends to make modules a bit more reusable than has often been the case. I noticed there was a question on the open spaces list outside about writing modules in a way that makes them reusable. So there's one way of doing it. If you're in AWS and you're taking advantage of the platform, then Lambda has become like this really useful additional control plane. So we don't generally need so the problem with self-healing, if you do everything via Terraform, is someone has to run Terraform periodically to make it work. So if you run provisioners to set up new instances or whatever, that's no use to you if an auto-scaling group replaces the instance. Right? So you can do all this stuff using provisioners, but Lambda's become this really nice event-driven control plane where you can delegate that away from your own infrastructure and just let AWS do it for you. I guess this is a Joyent connection. It wouldn't be that without showing some kind of node. This is a module which effectively watches auto-scaling groups for their notification, for their instance terminate, instance start. And it goes through the actually really nasty process, which they should just finish, of registering all of those with Route 53. So this was something you used to have to do on the instance itself. But of course, doing it on the instance has some serious downsides. It means that they have to have write access to the Route 53 API via their instance profile. And the instance profile is particularly badly protected in AWS because it's just available over unauthenticated HTTP. So if you have any kind of shared infrastructure on these things, then if you're running, say, Nomad clients and you have Nomad jobs from two different teams, then they effectively have a common set of AWS permissions. So you could use Vault to deal with that, but when it comes down to it, nothing's going to stop someone from curl 169.254 a couple of times, grabbing the instance profile credentials, and then doing whatever the instance has permission to do. So being able to move this stuff outside of the instance itself not only vastly reduces the amount of bash you have to write, although it replaces it with JavaScript, which I'm not sure is an improvement, but it also makes things a bit more secure because AWS is doing these things in their own control plane versus you doing them and providing the access needed to each instance. Lambda's Terraform support got a lot better recently. You can now set up complete, for anybody that tried that, like, say, a year ago, it was basically unusable because AWS didn't expose the right APIs. They now do. Terraform has now excellent support for Lambda. Okay. So one of the things I mentioned was, for production configurations, is that we want everything to be TLS encrypted. So I'm going to caveat this with this is probably not how I would do it in production. You can use Terraform as a certificate authority, which is kind of a lesser known feature. If you're going to do that, you really need to keep the state file secure somewhere. Do it on a disconnected box that's air-gapped from everything, and just take the keys, put them into Vault, issue certificates through Vault rather than issuing them through Terraform. But for the purposes of this demo, it's kind of the same thing, but without the extra step of setting up an air-gapped Vault. So the way Terraform can do this is by defining a root certificate and then a whole chain of intermediate certificates, eventually signing a server key and a server certificate. So this is what we can use to bootstrap Console with. So Console now has, in particular if you're on Console Enterprise, there's really good TLS support that replaces surf encryption and allows you to do proper rotation. But you need like an initial, you need something to TLS protect it from the start, and then you can rotate the keys out over time. So this is a great way of doing that. So the question then is, how do you get them up to the instances that are going to be started? Because of course they're auto-scaling instances. So while Terraform creates the auto-scaling group, it has no process. It has no place in creating the actual instances. So the answer to that is it's not terrible. It works. So if you encrypt the keys using KMS. So you create a KMS key specifically for this, encrypt them, preferably on your air-gapped machine or whatever. Then you can do like client-side encryption with KMS as well. If you encrypt them and then put them into an S3 bucket and give the auto-scaling instances for Console access both to the bucket and to the TLS decrypt operation, then it can pull down the secrets. They're still encrypted at rest, and you can control by locking down the IAM permissions for KMS, and for that key in particular, exactly who can do that. So this is a great way of solving the secret zero problem, if you like, without an operator being involved. It's probably something that you'd then rotate out for a Vault managed server key instead, so that you can make them much shorter lifetimes, and you don't have to deal with revocation lists and things like that. But this is a good way of bootstrapping it. If anybody's got any other interesting ways of doing that, then I'd certainly be interested to hear about them. And in particular, any equivalents for this on other platforms would be of great interest. How are we doing for time? Oh, 4 minutes. Okay. So all of this code is just available. I'm going to keep updating it as. So this is about the 5th rewrite of this code. As Console has grown features which make it easier to manage, for example, and Terraform has grown features which make it a lot easier to manage. It's no longer the same stuff that's in production. Well, it might be the same stuff that's in production at HashiCorp, I don't know. But if you're after sort of a guide to running these things in a reasonably production-friendly way, or after patterns that you can use for other infrastructure, then this might be a good place to look. So out of interest, did our server replace itself? So we have a new instance which is running. So we have 3 of them running. And if we go over here and console members, there we go. So the really important thing to notice here is that this 3rd server down says left and not failed. If it said failed, then that would still make it part of the quorum. So you have problems. But this actually appears to have worked fine. So if you have questions about any of this kind of stuff, then I'm going to be around. You either grab me or there's the open spaces. I'll probably hang out in the Terraform one, I guess. But you know, I really care what people want to talk about, so it's fine. Please look at the repository, pull requests accepted if you have things that you think can be improved, or you know, different patterns, or even different platforms. Different platforms would be really welcome to add to that. So with that, thank you, and I hope to talk to some of you during the breaks.